So hello everyone, welcome back to another particular lecture series of our Reagent Chemistry course, and this is the class 18. So in our previous discussion, we are completed all the organometallic reagents. So now we are talking about those certain different type of reagent that actually use for the epoxidation of double bonds. So initially we began with our discussion with the electrophilic epoxidation in this particular class. Then in the next class, we talking about some nucleophilic epoxidation reagents. So first of all, that oxidation of double bond, we are mainly focused on this particular reaction where the double bond or the olefins are actually in presence of the epoxidizing agents. It will generate this type of epoxides. So different epoxide generating reagents are there. So some of the electrophilic epoxidation agents and some of the nucleophilic one. So mCPBA is one, that the metachlorobenzoic acid, mNPBA metanitrobenzoic acid is there, DMDO dimethyl dioxide is there, Peracids are there. Peracids are nothing but this type of species where acetic acid is there. There is a one more oxygen is present there. This is called the Peracid species. Then H2O2, Br2 and sulfur halides are there. Okay. So this is the structure of metachlorobenzoic acid, and this is the metanitrobenzoic acid, and this is the dimethyl dioxide. So in this particular class, we are talking about these four today, and in the next class, we are talking about these three. So how this is actually used for the epoxidation, because this particular oxygen center are actually electron deficient. And due to this particular thing, due to the electron deficient, this all are called as the electrophilic epoxide generating reagents. So now let us begin with our discussion with the mCPBA. So mCPBA full form is the metachlorobenzoic acid, and this is the structure of mCPBA, and it's the electrophilic epoxidation agent. It is basically primarily used for epoxidation of alkenes. This is a double bond, and converting them into epoxides. This reaction is a selective with mild reaction condition, often in the DCM based reaction. Like in the DCM solvent, this reaction happens. And it is actually shows a broad substrate scope where works with a variety of alkenes, including electron-rich alkene and strained system also shown epoxidation in presence of mCPBA. But the catch of this particular mCPBA is it causes side reaction like Bayer vinegar oxidation, like in presence of this type of ketone type of system. This will show Bayer vinegar oxidation. That means this ketone to ester formation takes place. This is the side reaction. But in the case of normal olefins, basically the epoxidation is the major one. Okay, so now we are deep down on this particular mCPBA a little bit. So first of all, let us talk about the mechanism of this particular reaction. Like all the Peracid-based epoxidation can be done via butterfly transition pathway. So this is the butterfly transition. You can see that this type of transition is look like a butterfly. It is depicted here, and that's why it is called the butterfly transition. Now let us understand the mechanism in details. So this is the alkane. This actually, and this particular double bond is the electron rich, and this oxygen is the electron deficient. So what happened that this particular double bond is actually attacks here the electron deficient oxygen, and this particular bonds goes up. This particular then opens up, and this will try to capture this particular OH hydrogen here, and this bond are actually now comes here in oxygen center. So this will actually reversely attack in this particular electropositive center, and that's why it will generate this type of transition state. And this type of transition state is look like a butterfly that is actually depicted here. And this is called the butterfly transition state. And after that, bond breaking and bond prepare bond making takes place, and to generate, this is our the certain product, and this is the epoxide, and this is the acid is the our byproduct of this particular mechanism. And since it is a mCPBA, then it is called it will be the perchlorobenzoic acid, metachlorobenzoic acid is the byproduct here, and this the product is generated. And in the case of peracid, like if it is a peracetic acid, then the acetic acid become side product of the particular reaction. Okay. Now, if we talk about the regioselectivity of the particular reaction, then the more electron-rich alkane have the faster reaction rate with the mCPBA, because here the oxygen is the electron deficient. So, if the alkane are electron rich, then the reaction will be much higher, or the reaction rate will be much higher. For example, here you can see that the electron donating group in presence of a alkene, then it will have the higher reaction rate over electron withdrawing group. And this is regioselectivity can be observed in these examples also. Here is a normal alkane, and there is a substituted alkane is there, and this alkane are the electron rich. And due to this particular electron rich, is one equivalent of mCPBA will actually show epoxidation here, not here. So this is the regioselective reaction. Similarly, between this isolated alkene and this particular substituted alkene, here this has the more electron rich alkene is there. So the epoxidation has been observed in this particular center only. Now let us talk about the stereochemistry. So the mCPBA based epoxidation is a stereospecific reaction where mCPBA attacks from the less hindered site. So how it is stereospecific? As we know, stereospecific means the initial hydrogens are present here at the trans. After product formation, the hydrogen are actually in trans manner. Whether it is the epoxidation in the above the plane or below the plane, the relative stereochemistry between these two particular hydrogen is always same. Similarly, if the substrate contains the cis hydrogen, so after mCPBA treatment or the epoxidation treatment, the relative stereochemistry of these two particular hydrogen is always cis in nature. So that's why it is called that it is a stereospecific reaction. And also, second point is mCPBA attack from the less hindered side. So here you can find that this particular methyl are present in the above of the plane. So the mCPBA for the steric reason, this mCPBA attack from the less hindered side, so that the resulting epoxide is formed in the below the plane region. Similar trend has been observed in the case of bicyclic molecule, where the epoxidation will be from the less hindered side. So this is the bicycle molecule where the mCPBA, this particular conformer having the 99% selectivity, and this is the 1%. The reason of this particular high selectivity is when the mCPBA attack from this side, when mCPBA attack from this particular side. So what happened? The mCPBA will actually hindered by these two particular hydrogen present in the bridgehead carbon. However, if it is come from the lower side, so this will actually getting hindered from this particular two carbon CH2 pairs present in the lower direction. So in the lower side, the steric hindrance will be much higher than the above side. So the mCPBA will attack from the above side also, and this is the more favorable attack. And the bottom phase attack is disfavored. However, if this particular CH2, the hydrogen is replaced by a bulky group such as methyl and all, then mCPBA will force to attack from the downward side, and then it is called the major product. Endo product is major in presence of steric hindrance present in the bridgehead carbon. Also, the other electrophilic epoxidation agent, this is the other peracids like peroxyacetic acid, trifluoroperoxyacetic acid and peroxybenzoic acid, out of which this trifluoroperoxyacetic acid shows higher reaction rate over these two, because this will have the very high minus I effect, which actually makes this particular oxygen is more electrophilic in nature, and that's why this particular trifluoroperoxyacetic acid shows faster reactivity in terms of epoxidation reactions. And these three are also show similar type of reactivity as well as the similar reaction mechanism, just like mCPBA. Also here I want to show you about that how mCPBA reacts in presence of a Lewis acid. So mCPBA with Lewis acid often undergo ketone formation. So this is the alkane system. mCPBA doesn't react with the aromatic one. So this is the alkane one. Alkane one react with the mCPBA to generate the initial epoxide. Now this particular epoxide is actually this oxygen lone pair is donated to the BFP. This is the, and it will act as a Lewis acid, and then this type of intermediate is generated, and then Lewis SN2 mechanism has been observed. So this carbocation is generated, and after that this particular hydrogen transfer takes place, and then here a positive charge has been generated. Now this particular lone pair comes here to get their corresponding ketone, and this is the final product of this particular reaction. Next we talk about the another interesting electrophilic epoxide generating reagent. This is the DMDO. This is called the dimethyl dioxidant, and dimethyl dioxidant is a highly reactive and efficient epoxidizing agent, and it is actually generated in situ from acetone and potassium peroxymonosulfate. So sometime in the examination it is given as a DMDO, or sometime it will be given the mixture of acetone plus KHSO5. So if the both is are the same, DMDO and this both are the same, okay, and also it will be must be generated fresh, because the structure of DMDO is something like this. The structure of DMDO is something like this, and this particular cyclopropane ring is also there. Also this particular bond, this OO bond is not that much stable, so it will be can't prepare storable. So it will be generated in fresh, and it decomposes rapidly because of this particular ring rigidity as well as the weak OO bond. And it will provide exceptional selectivity, often related to fewer side products. And also it is useful for oxidizing sensitive or functional substrate due to its mild nature. So the reaction is something like this. So I just simply rub it out. So this is our alkene system. Alkene system react with the DMDO, where this particular is the del positive, and it will undergo also a butterfly transition state, and then we got our epoxide and acetone back. So this is the typical reaction of DMDO. So with this we have to end our electrophilic epoxidation or the all reagents. So in the next class we are talking about the nucleophilic epoxidation agents. So thank you for listening.